Yo, yo, yo! Welcome to CS50, Harvard, Artificial Intelligence, Chapter 3, Optimization, CrossWord assignment walkthrough. I'm Nick. I'm your host. You may notice something's going on with my eye. I won't tell you what it is. But we're going to be solving this problem by framing it as a constraint satisfaction problem. And it'll be solved using backtracking. So how do you get the most out of this video? Well, good news. It's packed with more than 20 diagrams and graphics. So you could really get the most by just watching it. You could watch it on the exercise bike, the treadmill, anywhere. But eventually you would want to follow along and type. But yeah, you can get value, big value, by simply watching it. So without further ado, let's roll! Okay, an incredibly high-level overview of what we're going to do. We start with an unfilled crossword puzzle and a bag of words. Each space where a word can fit is called a variable. Each variable maps to a domain, which is a bag of words that might possibly fill that space. When the program first loads, each variable's domain contains every word from our master bag of words. Next, our program will enforce node consistency. For our program, this means removing all the wrong length words from each variable's domain. You can see from this example that we've only kept words that have the same length as the crossword slot where they go in. Then, our program will enforce arc consistency using the AC3 algorithm. We recursively revise each word's domain by removing words that conflict on overlapping characters. This will become more clear when we code it out. For now, just take note that each domain was further reduced, almost to the point of already solving the puzzle. Finally, we will solve the puzzle using backtracking. The solution is output into this gorgeous PNG file that you can give to your mom. Buckle up, things are about to get ugly. So I've just downloaded the project file and opened it up with VS Code. I can see in the instructions that we run the project like so: Python generate.py, the name of a structure file, the name of a words dictionary, and then an output file. So let's take a look at the project and just get a little bit familiar with it. Our structure files are TXT files, and they're in this format where the underbars are spaces where letters can go, and the hashtags are walls or invalid tiles. Words 0.txt, 1.txt, and 2.txt are dictionaries, and they're essentially text files with a bunch of words separated by new lines. CrossWord.py is already done for us. It has two classes, variable and crossword. We're going to dive more into what each of those are, but we shouldn't have to touch this file, but we are definitely going to want to look at it. Generate.py, this is where all of our work will go. And we have one class, crossword creator, and then down here, the main function. And as we can see, we need all of these arguments, the ones specified in the instructions. And here our setups can vary wildly, but I'll just show you what I did, and you may or may not have to do something similar. I've set up a launch.json, and for the args, I'm putting the structure file, the words file, and output.png. I've had to set the current working directory. I made the program always be generate.py, so even if I'm on CrossWord, it's going to run generate.py, and I just gave it a name, sickpython. The other thing is I press Command-Shift-P to select an interpreter, and I've selected the Anaconda interpreter. You might not even have Anaconda, but I found this was something that worked for pillow. So I just did conda activate base and then conda install pillow. And I have pillow up and running. Then in generate.py, we need image, image draw, and image font from PIL, pillow. Now you don't need that to pass the assignment or start the assignment, so I wouldn't get too hung up on that, but to get the image to show up at the end, you will need pillow. Okay, now let's explore some of the guts of this program. So I'm going to jump into crossword.py, and again we've got class variable and class crossword. Crossword represents the whole grid, the whole puzzle. And let's kind of go through what these different things are really quick. I'm going to add a breakpoint there and run it. And let's first look at structure. So this is the crossword object, and here is structure. This is a 2D grid or a list of lists with a bunch of Boolean values, and they're populated by parsing that file. And this diagram kind of shows how they connect. These hashtags become false, these underbars become true, and I've made these graphical representations of a number of the things in this project, which I think make it a lot easier to grip. So treadmill people, this is for you. Next, let's look at variable. So on crossword, we have variables, and this is a set of variable. If we go up to variable, we can see that it has I, J, direction, length, and cells. And the direction is going to be either across or down. Best way to think of this is as a crossword slot. This orange box is a variable, and that is the one where I is 0, J is 1, direction is down, and length is 5. And there's the list of its cells. Variable. Next, let's look at overlaps. And I've had to step over a bunch of times to get this to populate from this breakpoint. So in self, overlaps. This is a double key dictionary where two variables form the key, and it maps to a tuple. It's easier to see in the diagram. So V1 and V2 have this overlap, and two variables can only have one overlap. So it'll either be a tuple or none. But the numbers in the tuple are essentially the index of the word for each one of these variables. So V1 is the across one right here. So this means that were the third or index 3 letters, so 0, 1, 2, 3, and then we're also index 3 down in V2, so 0, 1, 2, 3. So the overlap points to that green tile, but with the origin of these variables as kind of their reference. A little tricky, but it makes more sense with the diagram. And finally, let's look at neighbors. And you don't really need to worry about how this tricky generator works, but essentially neighbors is going to be all of the other variables that touch a given variable. So this 4, 1 across the orange box, if you call neighbors, it's going to give you these two, the two yellow boxes. And those are returned in a set. All right, then let's quickly jump into generate.py and look at CrossWord Creator. And this is going to be the main place where we're doing our work. And it has two member variables, CrossWord, which is an instance of our CrossWord class, and domains, which is a dictionary that maps each variable to a set of words. I can just quickly print self.domains and we can look at it, but initially it's going to start with all of the words for each variable. So there it is. We can see this variable 0, 1 down 5 maps to all of the words, and all of the other variables also map to all of the words. And beautiful. So let's code it. And we can just kind of do these right in the order that the instructions tell us, which means we'll start with enforce node consistency. And it says this function should update self.domains such that each variable is node consistent. And then each value in its domain is consistent with the variable's unary constraints. In the case of a crossword puzzle, this means making sure that every value in a variable's domain has the same number of letters as the variable's length. So I'm going to bang it out right now, which you'll see me do right now. So I'll get rid of the not implemented from enforce node consistency. And I'm just going to loop through the variables. So for variable in self.crossword.variables. And then I've got a comment. We only keep the words that are the right length for the slot or variable. And I don't like to remove while I iterate, so I'm just going to make a set to remove. So remove equals a set. And then for value in self.domains variable, if the length of said value is not equal to variable.length, remove.add value. And value right here is a word. And then finally, we can just say self.domains for variable minus equals remove. Alrighty, now that we've knocked down node consistency, let's begin to knock down arc consistency. When we talk about arc consistency, we're checking whether every value in one variable's domain is still compatible with at least one value in another variable's domain. Revise is going to be a helper function for AC3, which will attempt to achieve arc consistency. The revise function goes through each possible value of x, and it asks, can this value work with anything in y? In our crossword puzzle, there would be a conflict between a word in x and variable y if no word in y's domain had the same letter at the position of overlap. If there is no such word in y's domain, we can remove that word from x's domain. We will not modify y's domain. And finally, the function will return whether any deletions were made. So let's jump into the code, get rid of this exception, and you'll see me here banging it out. So we're concerned with the overlap. Let's get the overlap. Overlap equals self.crossword.overlaps xy. And if there's no overlap, if not overlap, then we don't need to revise anything. So we can just return false. No revision was made. Otherwise, we follow the pattern. Revised equals false. And at the end of it, we're going to return revised. We can unpack this overlap tuple into I and j. So ij equals overlap. And I'm going to again use this remove set. So remove equals a set. And then at the end of our loop, presumably through x and y, we're going to do self.domains x minus equals remove. Then let's just loop through all the words in x's domain. So for word x and self.domains for x, I'm going to make a variable called match exists and start it at false. Then I'm going to do some logic, and then if not match exists, there is no suitable variable or word in y, so we can say remove dot add word x, and then we did make a revision, so revised equals true. But what about this guts? What are these? What should go here? So we fill it in for word y in self.domains y, and we're just concerned with the letter at the point of overlap. So if word x at I matches word y at j, then we do have a match. So we can say match exists equals true and simply break out. We don't need to check anymore. And then we don't need to remove that word from x. And beautiful. Now that we've knocked down revise, let's knock down AC3. So AC3 is an algorithm that checks all pairs of variables to make sure they remain arc consistent. It works by putting every arc into a queue and then pulling them out one by one to see whether the first variable still has values that match with the second. If a revision removes values, the algorithm re-adds related arcs back into the queue, and those arcs will be checked again. And then if any variable ever loses all of its possible values, then it is an unsolvable problem. So let's bang it out. You'll see me bang it out right here. For my queue, I'm going to use a decay way. So up at the top here, I'm going to say from collections import dequayway, and then jumping down to AC3, we just have to follow these rules. So if arcs is none, begin with the initial list of all arcs in the problem. Otherwise, use arcs as the initial list of arcs to make consistent. So if arcs is not none, then for arq, we can create a dequayway. Oh, there should be is not none. I'm sorry. So q equals dequayway of arcs. Otherwise, we want all arcs in the problem. And the arcs are going to be every variable paired with every neighbor of that variable. And I have this very sexy generator function or generator expression. So q equals dequayway of xy for every variable. So for x in self.crossword.variables, and then for y in self.crossword.neighbors of x, and now that we've populated our dequayway, we can enter the main body. So while q, we'll pop the q, so xy equals q dot pop left, and then we're going to try to revise xy. So if self dot revise xy, we've changed x's domain. So if it became empty, the problem is unsolvable. That means if the length of self.domains for x became 0, we simply return false, not solvable. Otherwise, we add the related arcs. Related arcs is a bit of a weasel language. So we can say that when we revise xy, it changes the domain of x. So we recheck all other variables that depend on x. And we denote that as z. So for z in self.crossword.neighbors of x, except for y, so we can minus the set with just y. And be careful that you don't say set y, because that is not the same. All right, then we add all of those zx arcs. So q dot append zx. And if we haven't returned false, at this point, it is arc consistent, so we return true. And we can say, yay, arc consistent. And next on the list is assignment complete. This is just going to check essentially if there is a word in every slot. So a word mapped to every variable. And it's a little bit confusing because we haven't created any kind of assignment yet, but just bear with me. So that assignment variable is a dictionary where the keys are, again, variables, and the values that the keys map to are words. So let's just go ahead and knock it down. If it's complete, that means there's going to be one assignment for every variable, and we can just check that by comparing lengths. I'm just going to paste in my comment. There should be one assignment for every one of the CrossWord's variables. So if the length of the assignment is not equal to the length of self.crossword.variables, return false. It is not complete. Otherwise, I think what I've done is just been overcautious, but I would still recommend to be overcautious. So here's my comments. Every assigned variable must appear in the CrossWord's variables, and every word in the assignment must be valid. So let's go ahead and do that with a little loop. So for variable in assignment, if variable not in self.crossword.variables, return false. And then if for some reason there's junk in the assignment for that variable, so if assignment variable is none, then we would also return false. But as I say, I think that's a bit overcautious. And then finally, just return true. And it won't tell us if the assignment is correct, just complete. Super. Now let's look at the consistent function. And this takes the same argument as assignment complete, which is this assignment dictionary. It's important to note that the assignment may not be complete. So it could be a partial assignment, and this bullet here really sums up what it needs to do. An assignment is consistent if it satisfies all of the constraints of the problem. That is to say, all values are distinct, every value is the correct length, and there are no conflicts between neighboring variables. So let's bang it out. You'll see me bang it out right here. So just watch. All right, I'm gonna translate those conditions into comments, those 3 conditions. So that's pretty much what we're gonna check, and we'll do kind of false checks on them. And if none of them return false, we'll return true. So that'll be the pattern we follow here. The first condition, all values are distinct. This is kind of straightforward. Essentially, just every word should be unique. In other words, there should not be duplicates. So I'm going to define a helper function called contains duplicate for elements. And I just want to see, and that's going to be a list. So I want to see if the length of the list is the same as the length of a set of those elements. And this is contains duplicates. So if it does not contain duplicate, so just return length of elements is not equal to the length of the set of the elements. And then we have to call it on the words. So remember, assignment maps variables to words. So these are the values of the dictionary. So if contains duplicate assignment.values, then it is not consistent, return false. All right, every value is the correct length. This should be no problem for us. So let's loop through all of the variables or the keys. So for variable in assignment if the length of the assignment for said variable is not equal to variable.length, return false. That word is the wrong length. And finally, the hard one. There are no conflicts between neighboring variables in the assignment. And I'm going to set this up kind of as a nested loop. So for variable A in assignment, I'm going to loop through all of its neighbors. So for variable B in self.crossword.neighbors for variable A, first of all, variable B needs to be in the assignment. If it's not in the assignment, then it doesn't matter if it's consistent. So we can say if variable B not in assignment, just to continue. Otherwise, we need the overlap. So we'll say overlap equals self.crossword.overlaps of variable A and variable B. And similar to what we've done before, we want to check if this overlap even exists. So if not overlap, then there's definitely no conflict, so we can just continue. Then we're going to want the words from the assignment. So word A equals assignment for variable A, and word B is the assignment for variable B. And then we can unpack this tuple again. So ij equals overlap. And then finally, if word A of I is not equal to word B of j, these are not consistent. So we have an O on a Q tile or something to that effect. So we can return false. And I'll just compress this a bit. Yay! Another one. All right, let's do order domain values. The goal of order domain values is to apply the least constraining value, or LCV, heuristic. For a given variable, we look at each possible word and ask, if I choose this word, how many options does it remove from my unassigned neighbors? Values that rule out fewer neighbor choices are considered better, and those should be earlier in the list. Any variable that is already assigned can be ignored in this counting because it has a fixed value and is not part of this decision. So now what you're going to see, I'm going to bang it out. So what I want to do is rename var to variable A just for naming, just so I can have this variable A, variable B nomenclature. So I'm going to say variable A equals var. And now we want variable A's unassigned neighbors. So LCV only considers how our choice affects unassigned neighbors. So unassigned neighbors is, we'll use a list, neighbor, and this is going to be the neighbors not in the assignment. So the neighbors for neighbor in self.crossword.neighbors of variable A not in the assignment. If neighbor not in assignment, then I'm going to use a dictionary for these rule out counts, and it's going to map each word in variable A's domain to a conflict count. So rule out counts is a dictionary. And then we're going to kind of loop through all of these words. So loop through every possible word for the chosen variable. So for word A in self.domains for variable A, I'm going to get a rule out count. So not counts, but just count. Rule out count equals 0. Then some logic, and then I'm going to stick it in the dictionary. So rule out counts for word A becomes this rule out count. And we'll come back to that. But for now, assuming we had the rule out counts, let's go ahead and sort the list and return that. So return value sorted so the least constraining word comes first. And for this, I'm going to use a lambda, and I'll just call it sort key. So sort key equals a lambda with a variable that just counts or just uses the rule out counts for said variable. And finally, return sorted of self.domains for variable A, and the key is going to be sort key. All right, but what about the middle? So I made a comment that's going to add some clarity here. For each unassigned neighbor, check how many of its words violate the constraint. So now we're talking about the neighbors, and we already have those. So for neighbor, or actually I'm going to call it for variable B, for variable B in unassigned neighbors, this is another one of these overlap things. So let's get the overlap. Overlap equals self.crossword.overlap for variable A, variable B. And another comment, if there is no overlap, therefore 0 conflicts between the variables. So if not overlap, then continue. And I guess this comment should go inside of the not. And now it turns into a hairy boy. Well, but first let's just unpack this tuple. So ij equals overlap. And here's our hairy boy, a triple nested loop. So count how many of the neighbor's words disagree with the overlapping letter. So we're going to be looping through variable B's domain. So for word B in self.domains of variable B, we're just going to increment the rule out count if they mismatch on that overlap tile. So if word A at I is not equal to word B at j, then rule out count plus equals 1. That's a naughty hairy boy. So let's just compress this. Next on the list is select unassigned variable. The select unassigned variable function should return a single variable in the crossword puzzle that is not yet assigned by assignment, according to the minimum remaining value heuristic and then the degree heuristic. So we have these unassigned variables. We could just pick randomly, but this is Harvard, so we're going to put in more effort. So let's just jump in. You're going to see what you saw, which is me banging it out. So I'll be here right now doing the thing. So watch, do it yourself. All right, so unassigned variables. That's easy to get. We want to collect all variables that do not yet appear in the assignment. So the variables are the crosswords variables, and then these are the keys. So remember, assignment maps variables to words. So unassigned variables equals a list, and we can just use setmath self.crossword.variables minus assignment.keys. So those are all the unassigned variables. And then we need our two heuristics. So first, the MRV, minimum remaining values heuristic. So I'm just going to call it remaining values, and this will be a dictionary mapping every variable to essentially the length of the domain for that variable. So the length of self.domains for said variable for variable in unassigned variables. And then the degree heuristic. The degree is the neighbor count. So let's go ahead and populate degrees equals a dictionary, again for variable as the key to length of the neighbors is self.crossword.neighbors for variable in unassigned variables. And then we want to sort ascending by remaining values and descending by degrees. So we can just use negative to do descending. So I've made a comment. Select the variable with as priority 1 the fewest remaining values, and priority 2 the most neighbors. So I'm going to make a key. So sort key is a lambda for variable, and I'll break this up onto a couple lines with our two heuristics, and the order will be first remaining values for said variable, and then descending, so minus degrees for said variable. And we're only picking one. So if we return sorted, the sorted list of unassigned variables where the key is sort key, we just need the first item from that list. But instead of doing sorted, we can just return the min. Now the instructions say that we could use sort, but I find this is a lot better. So min. And now for our magic moment. This magic moment. Backtracking, oh my God. All right, so let's wrap it up with backtracking. Backtracking is just a smart trial and error search. We try filling the crossword step by step, and whenever something becomes intractable, we undo that choice and try a different one. Our assignment is simply a dictionary mapping each crossword slot to a candidate word. At the start, many slots aren't filled yet, and our job is to grow this assignment until every slot has a word. A satisfactory assignment means two things. All the slots have words, and all constraints are respected. Words must be the right length. No two slots use the same word, and no overlapping letters must match. If no complete assignment is possible, then it is not possible. We return none. All right. Now I'm going to surprise you and do my thing. I'm going to bang it out. So this is a recursive function. First of all, let's get rid of this. Don't want that. A number one, if it's complete, we're done. So kind of working backwards, but if the assignment is complete, we've succeeded. So if self.assignment complete for the assignment, then we can return the assignment. Then we're going to be using all of our labors. So the first one we're going to use, select unassigned variable. We're going to smartly select a variable to assign using the MRV and degree heuristics. So I'm just going to say variable equals self.select unassigned variable for assignment. Then we're going to again use the fruits of our labor and try the values in the least constraining order using our order domain values function. So for value in self.order domain values for variable and assignment. And backtracking kind of works like this. We're going to first tentatively assign the value, and then if it didn't work, we're going to unassign it. So to assign it, we're just going to say assignment for the variable equals value. And to unassign it, we're going to do something I rarely do, but just use the Python delete. Delete assignment for variable. But what about the middle? So what goes here? I've got a comment that is just what you need. If this partial assignment is still consistent, recurse. And luckily, we've already got that ready to go. So if self.consistent, the assignment, then we can say our result equals self.backtrack assignment. and then if result, we don't want to compute it twice, and we can just return it, return result. But what about the end? What if we didn't return anything? Well, we flubbed. No good, return none. And actually I've got a little comment. No solution was found. Harakiri. So we die the honorable death. And that should be it. Let me run it. And it worked. So there it is, output.png. Congratulations. And you should note, this isn't really how you program. It's very rare to do something so linearly. But you had a helping hand. So awesome. Again, congratulations. If somebody says this isn't real AI, they're not a real person. They're a phony.